stuff in your calculator. That'll be more helpful. But that's essentially how you want to do it, right? Keep track of the steps that you do to get that first, or this overall, and then just do that to the K value. Okay. I think it's kind of fun. It's like a little puzzle, but maybe you and I have different versions of fun, and that's A-okay, and I love that. All right, so consider the following reaction and corresponding value of Kc. So I have H2 plus I2 to form 2HI. That's it. So it has a Kc of 6.2 times 10 to the 2 at 25 degrees Celsius. What is the value of Kp at this temperature? So you can link Kp and Kc, which is, this is going to be the equilibrium constant for, pressure, and this is going to be the equilibrium constant for concentration. So they're linked by this equation, which is Kp equals Kc times RT to the delta N. And this R right here is going to be my ideal gas constant, which is 0.08206 times liters times ATM over mole per times degree Kelvin. And so this is naturally has to be in degree Kelvin. And this N right here is going to be the change in moles. So we know delta is essentially final minus initial. That's what a delta means. So basically the change, so the final minus initial, in the number of moles on each side. So what you want to do is count the number of moles on each side of the reaction. And so basically you want to do products minus reactant. So to count the moles, I'm going to look at the coefficients. Okay, so there's 2 on the right, so that's 2. Okay, let me look on the left. There's 1, 2. These don't have any coefficients, so I just add them. So 2 minus 2 equals 0. Okay, so when I plug in, so I have Kp equals Kc times the 0.08206 gives, oh, let me remove that parentheses because I need to make sure I include temperature, so 298, and so raised to the 0. Remember from when we did reaction orders, anything raised to the 0 is going to be equal to 1. So that just sort of eliminates itself, right? So Kp is going to be equal to Kc. So you can generalize this. So if delta N equals 0, then Kp will equal Kc. Fun stuff. I missed that on my chemistry exam when I took the class, so pay attention to that. All right, so number 20 says you are given the initial concentrations of carbon monoxide and hydrogen gas. At equilibrium, the concentration of CH3OH is 0.11 molarity. Find the equilibrium constant at this temperature. Okay, so what you want to do is look at this overall equation. And I like to set up ice tables by writing the equation above it so that I am not confused, I know what's going on, and I keep the reaction in mind. Okay, so what I want to do is I write out my ice tables, which they don't go away, they never do. So these are pretty much like the rest of Chem 2, so I hope you like them. So I want the initial concentration, the change in concentration, and then the equilibrium concentration. So it tells me that I start at 0.27, so I'm going to write 0.27. All right, it tells me that I start at 0.49 of H2, okay. And then, given that it doesn't say C3OH, I'm just going to write 0, right? Because that assumes that there's nothing in the cylinder to start. There could be, just pay attention to that. It's not always going to be the case where the product concentration starts at 0, so just be aware of that. So it tells me the equilibrium, the concentration of C3OH is 0.11. So I'm just going to write the equilibrium concentration in, right? So that was an addition of 0.11 molarity. So now these had to have decreased because of the reactants. And so I want to look at these coefficients when I'm considering this. So if CH3OH increased by 0.11, that's got to mean that carbon monoxide decreased by 0.11, so that gives us 0.16 at equilibrium, okay? And so that means I have to take into consideration that to form 0.11 molarity of C3OH, I had to have reacted 0.22 molarity of H2, so minus 0.022. So when you subtract that, you get 0.27 molarity. So to find the equilibrium constant, now you just plug into that law of mass action, which is going to be my products over reactants. So I'm going to put the equilibrium concentrations in there. So remember my product on top times my reactants. So 0.16 and then 0.27 squared. And that's going to give me my equilibrium constant at this temperature. Which, once again, I did not do it the math for my calculator, so practice getting stuff in your calculator thine self. Because I find that a lot of students will have the process completely down, and they have all the math, but it really comes down to calculator errors. So make sure you're confident with that, and you're doing some work. All right, so it says consider the reaction below. 2H2S to form 2H2 plus S2. So it gives me a Kc of 1.67 times 10 to the negative 7 at 800 degrees Celsius. And it says, given the initial concentrations, find the equilibrium concentration of S2. So I'm going to set up my little handy dandy ice table, but I'm going to write out my equation on top. So 2H2S to form 2H2 plus S2. Cool. So now I'm just going to write my little columns. Oh, that's not a column. Let me start it right there. There we go. So I'm going to have initial, change, and equilibrium. So I, C, and E. So it tells me that I start at 0.1 H2S, so 0.10. All right, so then I have, let's see, I have to start 0.1 of H2, and it says that I have none to start of S2. So I don't know how much it changed, so I'm just simply going to say minus 2x, right? Because whatever it decreases by, this coefficient is going to dictate. All right, so what I'm going to do here is minus 2x, and then I'm just going to put plus x. So then when I write the equilibriums, I'm going to do 0.100 minus 2x, 0.100 minus 2x, and then I'm just going to put x right there. So now I'm just going to sub into my values up here, which I'm going to have my products on top. So it's going to be 0.100 minus, or well, plus 2x actually, plus 2x times x over 0.100 minus 2x. And now this looks intimidating, and you would have to use the quadratic formula, but I know you can use the small x approximation to conclude that essentially the x does not matter. So for this, I essentially want to equal it to that Kc that it gives me, which is that 1.67 times 10 to the negative 7. And so I'm going to pause right here, and then I'll start up my next video. Okay, I'm starting up with part 4 of my exam review. Something I added here was I forgot to add the exponents, so I made sure to add the exponents there, but using the small x approximation, I can cross out these x's right there. So I essentially bypass having to use the quadratic formula. So what I end up with is 0.10 squared times x over 0.10 squared. So I can essentially simplify and eliminate that. So then I just have x equaling 1.67 times 10 to the negative 7th. Okay? Pretty straightforward. Don't get too spooked by it. So the next problem, which is given the following reaction, is endothermic. Describe the shift, left, right, or no change. Okay, so let me write my error right there. So the reaction of N2 plus 3H2 to form 2NH3. So this is going into Le Chatelier's principle, which is essentially our reaction at equilibrium has a tendency to want to move back to equilibrium. So it'll do whatever means necessary to get back to that equilibrium constant, which you know is that K, right? Because we know if our Q equals K, then we're at equilibrium. So naturally it wants to go back to that. So starting out with A and B, what you want to do is I like to consider heat as its own product or reactant. And remember, something that's endothermic, I have to add heat to make the reaction start. So I consider something that's endothermic to be a reactant because I have to add it to the reactants to make the reaction proceed. versus something that's going to be exothermic. It's going to release energy. So something that releases energy can also be considered a product, right? So if I remove heat, so like in part A, if I remove heat, that's essentially removing a reactant. So to compensate for that, the reaction is going to go to the left. Similarly, if I add heat, that's the same thing as adding a reactant. So it's going to push to the right. So similarly, if I add NH2, that's like adding a reactant, so I push right. If I remove well, this should be NH3, sorry there. If I remove NH3, I'm going to push it to the right as well, because now I'll have a larger denominator than numerator, right? So I need to push back up and add more product, and to do that, I push it to the right. So let's say I remove H2, which is removing a reactant. I'm going to move to the left. So now F and G sort of come into the concepts of how pressure and volume affect Le Chatelier's principle. So volume, it's going to have the tendency to go where the least or most moles is, depending on what you do. So if I decrease the moles or decrease volume, I'm going to go to the side with least moles. And I use that by counting the coefficients in the molecules. So if I increase volume, I'm going to go to the side with the most moles. So if I decrease my volume and I'm going to go to the side with the least moles, I'm going to count my reactants and products. So what I want to do is I look here. All right, so on the left, I have 1, and then I have 3. So it's going to be 4 on the left. If I look on the right, I have 2. So if I decrease my volume, I'm going to want to go from more of my reactants to more of my products, meaning I'm going to shift it to the right. If I increase my volume, I'm going to want to go to the side that has more moles, so I'm going to want to shift to the left. So that's going to be a shift to the left. And now because that's bothering me, I want to make sure this is in blue as well. So similarly, I can relate pressure and volume. So I have pressure. Well, we know that increased volume equals a decreased pressure. We know that they're inversely related, right? So if I have a pressure increase, I'm essentially pushing down. Let's say they're all in some cylinder, all in some container. I push down in that container. I'm decreasing its volume. So if I increase my pressure, I'm going to go to the side with the least amount of moles. So a pressure increase is also going to be a shift to the right in this case. If I have a pressure decrease, I'm increasing my volume, meaning I'm going to go to the side with more moles. So in this case, it's going to be the left. Without a doubt, you'll have a question like this. You'll definitely have questions on the ACS, and if you're like pre-med, it comes up with MCAT prep. So I would pay attention to Le Chatelier's principle. It comes back in biochem. So don't be scared of that. Let's see. Yeah, I guess I'm finished. If you have any questions, feel free to reach out on the web courses. I'm not going to be doing chapter videos for all of the chapters. I simply can't keep up with that. But I'll definitely be doing exam reviews, and then I'll have a video up on chapter 12, or like this is crystalline solids, coming up shortly. But feel free to message me if you need any help. I have a session Wednesday morning at 8 a.m. and then Thursday morning at 8 a.m. So right before your exam. And we're literally right next to the exam room. So it'll be Thursday, 8 a.m., my little early birds, at CB1, room 117. So if you want to come out right before your exam and have any final questions answered, feel free to come out. We'll work together. If anything else, just message me on SARC or on the SARC web courses.